automatically generating convex regions for agent navigation in virtual worlds. In most virtual environments, the only information you have about the world is the location of the geometry that comprises the physical layout of the environment. This makes sense, as the geometry will be rendered to the screen and seen by people, as well as being used for collision detection with dynamic objects. Collectively, the areas occupied by geometry representing objects can be referred to as positive space. In this video, from our Urban Combat Testbed game environment, you can see an agent moving through a 3D environment composed of geometry. However, there's a problem with this representation of virtual environments. AI agents do not really see and interact with occupied space. Rather, agents spend all their time in the open spaces between the positive spaces. This open, unclaimed space is referred to as negative space. While every rendered virtual world, by definition, contains a nice, concise, enumerated listing of positive spaces in the form of the geometry that creates these objects, no such inherent listing exists for the negative space unless it is explicitly generated. Generating a partitioning of negative space in the form of a navigation mesh provides several advantages to agents. It aids in movement by producing a simplified path planning graph to search over. Collision detection can be managed and localized by examining only objects located in the same or neighboring regions of the navigation mesh. And finally, it assists in agent reasoning by compartmentalizing and limiting the areas and the objects contained within they have to reason about.
We present our new decomposition of environments for the creation of convex region navigation meshes algorithm called Deacon for short. Deacon provides us with a new approach for generating navigation meshes from world geometry. It initially drops a grid of unit-sized quads into the geometry to be decomposed. In this video, the positive spaces are outlined in gray. Defined negative space regions are represented as the growing colored areas. One of the first advantages provided by Deacon is the ability to generate a higher coverage of the environment by self-seeding additional regions when one of the pre-existing regions is prevented from further growth but is still aware of nearby open space. This form of self-seeding provides a more complete navigation mesh than would be possible with more traditional algorithms. The most unique portion of the Deacon algorithm involves its reaction to encounters with the geometry. When a vertex of a region encounters a piece of positive geometry, an effort is made to split that vertex apart so that the order of the polygon increases. This then allows the region to better approximate the negative space we are trying to decompose and to continue growth in new directions. Using this technique allows us to fill up negative space with fewer but higher order convex polygons. This in turn reduces the complexity of the navigation map we are trying to build and avoids many of the triangle-based problems that appear in the Hertel-Melhorn algorithm. Our implementation also provides several ways to manually influence and direct the growth of these navigation meshes. The density of the initial seeding can be adjusted both up and down. Offsets can be added in the X and Y direction to produce different growth patterns. The maximum order any growing polygon can achieve can be limited to fixed values. We can also choose the manner in which seeds are automatically generated from growing regions. By exposing so much of the controlling algorithm to the user, our Deacon implementation allows a level designer or AI developer to generate several decompositions for their geometry and then choose the one that best suits their needs.
Deacon has been utilized to generate automatic decompositions for several game environments. In addition to the Urban Combat Testbed game shown previously, the Skookum game, which you are now seeing, implemented its AI navigation and path planning, as well as its collision detection using Deacon-generated navigation meshes. Using a simple plugin, this was implemented in less than an hour. Each level decomposition for Skookum took less than 5 minutes. In conclusion, Deacon is considerably faster and provides better decompositions than other methods of generating navigation meshes. It provides complete tunability to desired decomposition characteristics.